Hi, this is Barrett Givens, and in this video, I'm going to talk about set builder notation. So set builder notation is a way of writing sets that many people have told me they find sometimes confusing. So what do I mean by set builder notation? Set builder notation usually has a format that looks like the set of all little a in capital X such that some property of A holds. Okay. And so when we write it this way, the format is that the whatever's over here on the left, this would be the elements of your set. These are the elements of your set. And then this capital X right here, sometimes that's not always included. That's sort of optional, but this is the universe the elements come from. And then finally, over here on the right, we have the property that must be true to be in the set. Okay. So, all right. And so when you're trying to figure out, if you have something in set builder notation, you're trying to figure out what are the elements of that set. You have to think about if those elements were to sort of equal to A, and then you look at the property A and decide, is that property true or false? And if the property is true, then the A that you're looking at is in your set. And if the property is false, then the A that you're looking at is not in the set. So let's just do some examples. I think that's probably the easiest way to understand what's going on. So here's an example. Let's look at the example of the set of all x in Z such that x divides 12. So divides here means x goes into 12 evenly as a factor, okay? So the elements will be possible integers. And let's say I want to know, let's call this set A. Which of the following are elements of A? Okay, so let's say x equals 2. Is 2 a factor of 12? Does 2 go into 12 evenly? Yeah, 2 goes into 12 6 times. Yes. Okay. What about x equals 5? Is 5 a factor of 12? No. So 5 is not in the set. So 2 is in the set and 5 is not in the set. Can you list all the elements of this set? Can you list all the elements of this set? So I think in this case, the elements would be, well, what are the numbers that go into 12? 12 goes into 12, 6 goes into 12, 4, 3, 2, 1. Does 0 go into 12? I mean, that's a topic for number theory, but the answer is no, it does not. So maybe we're just done here. It's kind of a trick question. There's also the negatives of these. Okay, so this is what A actually equals in this case. So the idea is for each number, I thought about, okay, if I wanted to look at the number 12 here, if I wanted to look at the number, well, let's look at the number 6. If I looked at the number 6 here, I would sort of mentally make 6 equal to x, and then I would look at this statement here and I would say 6 divides 12, true or false? True, therefore 6 is in the set. Okay, so again, the thing on the left is what the elements will be equal to, and then the thing on the right, the thing on the left here, this is what the elements are equal to, is little x's. And then the thing on the right is the statement that you have to decide, is it true or false when you put in that value for x? Okay, so let's go to the next example. Let's call this one B. B is the set of all x squared such that x is a real number. So here again, the elements have to look like, the elements have to equal x squared. and then this must be true. So I could list some elements here. I could list some elements. So for example, 1 squared is 1. 1.5 squared is 1.25. Pi squared is whatever pi squared is, okay? So there's a lot of possible numbers. Oh, negative 12 squared is 144, and so on. So there's a lot of elements in B. All of these are elements of B. These are all elements of B. Because in each of these cases, if I were to let like 144 equal x squared, if I let 144 equal x squared, then I could say x equals 12 is one possible answer to that, and 12 is a real number. True. Okay? So the thing on the left is what the elements have to equal. And so this tells me that 144 is an element of B. Is 12 an element of B? I almost confused myself there. I almost couldn't decide. Is what I just showed here. This is showing that 144 is an element of B. Is 12 an element of B? Yes, because 12 is equal to 2 root 3 squared. So 12 is an element of B. Is every real number an element of B? Is every real number an element of B? What if I tried to think about negative 1? So that would mean I would need to be able to make negative 1 equal to what the elements are supposed to equal. So I'd have to say negative 1 equals x squared. If negative 1 equals x squared, what could x equal? Is there a real number that makes x squared equal to negative 1? No, you could either say, well, there's no reals that make that true, or you could say, oh, well, the only numbers that make that true are I and negative I, which are not real numbers. Okay, so basically this is an imaginary number that makes this true, but there's no real number. So if x squared were equal to negative 1, then x being an r would be false. And so that tells me that negative 1 is not in B. Okay, and a similar argument works for all the negative numbers, right? For any possible negative real number, it's not going to be in B. What about 0? Is 0 in B? If I let x squared equal 0, is there a real number x that makes that true? Yeah, 0 squared. So in this case, I think that B in interval notation, B is the set of all numbers greater than or equal to 0. Okay. If I wanted to write it in set builder notation, B is the set of all x in R such that x is greater than or equal to 0. That's another way to write B. So these are all 3 different ways to write the set B that are all the same. Okay, let's do another example. Let's call this set C. C is the set of all x comma y in the plane R2 such that x squared minus y squared is greater than or equal to 1. So our universe now here is the plane R2. So R2 means xy axes, and the points are ordered pairs. Okay? Is 0, 0 in C? So I would try plugging 0, 0. So this means that I'm going to let xy equal 0, 0, plug it into the condition on the right-hand side, 0 squared minus 0 squared. I'll put a question mark over it, greater than or equal to 1? No. Can you think of some point that's in C? Just any point that's in C. I mean, there's a lot of answers. I like maybe 1, 0. So that means I'm going to imagine 1, 0 equaling this thing. If I let 1, 0 equal the thing on the left is 1 squared minus 0 squared greater than or equal to 1? Yes, it's actually equal. So 1, 0, which is right here, that point is in C. What about 0, 1? Well, I would say 0 squared minus 1 squared, question mark, greater than or equal to 1? No, that's -1, which is sad. So that's not in there. Okay. So in this case, I think if we actually think about what's the set of all x squared minus y squared equaling 1, and you may remember from the mists of time from like a calculus class maybe, or even a pre-calculus class, that this is a hyperbola. So the set of all points such that x squared minus y squared equals 1 looks sort of like this. Okay. So all those points make x squared minus y squared equal to 1. And then you kind of have to think about, so x squared minus y squared is greater than or equal to 1. That means the x part has to be bigger than the y part in absolute value. Okay. And so you could sort of convince yourself that that means you should shade everything out here, and then you should shade everything out here. And so capital C is the shaded region along with the edge. Okay, because it said greater than or equal to. All right. Finally, I have two last examples. These two examples are going to involve sets of sets, okay? Sets of sets. And so that just tends to confuse people. So here, the elements of my cursive B1 look like the form of capital B subset of Z, such that B complement is finite, union the empty set. So my first question is empty set in B1? Yes, because it's in here, right? There it is. Look, I see it, okay? And that's being unioned with this other more complicated thing, so yes. All right. What about, is the set of all even numbers, which I could write this way. -2, 0, 2, 4, 6, ... in cursive B1. So first, it has the right form, because the form of things that we're trying to think about being in B have to be subsets of the integers, and this is a subset of the integers. What is the complement? So we have to look at the condition now. The condition that we have to ask, is this condition true or false? If I make this thing, if I call this thing right here a B, and then I put it into this spot right there in that statement, is that statement true or false? B complement would be the set of all odd numbers. Is that a finite set or an infinite set? That's an infinite set. So in this case, the complement of the even numbers is the set of odd numbers, which is not finite. And so the answer here is no. Okay. What about, is the set B equal the set of all non-zero integers in fancy B1? So again, now I'm going to take this new capital B that I have, this new capital B, and I'm going to sort of say, okay, first of all, is it the right sort of set? Well, it's a set of integers, so that's the right universe that I'm living in. And then I have to look at this statement about the property that it should have. So what is B complement? B complement, the set of all non-zero integers. So what's the integers that are not non-zero? Not non-zero would mean 0. So B complement is just 0. Is that a finite set? How many elements does that have? 1, which is a finite number. Okay, so that only has 1 element, so that is finite. And so this one, I would say yes. Okay, so in general, if you think about it, you can kind of see, in general, elements of script B1 look like, they have to look like Z minus just a few things in 1, in 2, in 3, up to nk. So z with just a finite number of things taken away. So like in the second example was the one thing that was taken away was 0. Here, maybe we could take away 1, 3, and 5. Then that would be in fancy B. All right. And then one more. Let's let B2 be the set of all intervals closed at A and open at B as subsets of R such that A is less than or equal to B. Okay. So let's just draw one of these. Here's A, here's B on my real line, and it's closed at A, open at B. So this is like a typical element of this set. Okay. Is 3, 4 in B2? So you ask yourself, if 3, 4, if I were to sort of like think of this as AB here, is A less than or equal to B? 3 is less than or equal to 4. Yes. Okay. Is 3, 4 union 5, 6 in B2? So if I were to try to think of this whole thing as having the form A comma B, well, sadly, it doesn't have that form, right? It doesn't have the right form. So that's no. We don't even really get to the point of asking is A less than or equal to B. You just can't write it in that form. But now this is a trick question, because what about if I do 3, 4 union 4, 5? Let's draw both of those. The one above that's not in B2 look like it's a solid circle at 3 and an open circle at 4 and everything between, and then a solid circle at 5 and an open circle at 6 and everything in between. Okay. And then this one looks like 3, 4, 5. Solid circle at 3, open circle at 4, unioned with solid circle at 4, open circle at 5. So it turns out that this one can actually be simplified to look like 3, 5. So it can be rewritten to match the form that we're expecting to have. The form up here that all of these sets have to have looks like this. It can be rewritten in that form. And is A less than or equal to B? Yes. What about is singleton 3 in B2? Just the point 3. This is like a little sketchy. It kind of depends on what you allow for your interval notation. But I would say that this actually looks kind of like 3, 3. And so if this is AB, is A less than or equal to B? Yes. Okay, so I would say that is in B2. All right. That last example, you should know that some faculty would consider that this is just not something that you're allowed to write. So some faculty might say, Dr. Givens, what are you doing? That's not correct. And other faculty would say it's fine. It's kind of a judgment call. It kind of depends on the class. So you should definitely, if ever anything like that comes up in a class and you're not sure, that's something that you should ask the professor because it does vary from book to book, from class to class, or from faculty member to faculty member. And I'm not even sure what I think. I might think that that's actually not allowed. I'm kind of debating. But if you did allow it, then the answer would be yes here. All right. So that's kind of some examples of set builder notation. It definitely can be confusing. Like it seems like a very simple thing, but then there's so many different ways that they can turn up. And so you just have to really take it slow and remember that the elements in your set builder notation are the things on the left, And the condition that you have to check if it's true or false is the thing on the right. All right. Thank you so much for listening.